Hello and welcome back. In this video we're talking more about continuity of functions of two variables, and indeed several variables. Um, we're going to build up what we know to be continuous functions, ways to find out a function is continuous without necessarily computing limits. So sort of the easy case is how do we know if those functions are continuous? One way to build up functions is through composition of functions. So here we have a theorem, and this is proved using the definition of continuity and the definition of limits. This can be proved. So what it says, if I have a composition of functions, like f of g of xy, so I apply g and then I apply f to that, well, that's continuous so long as g of xy is continuous at that point and the outside function is continuous at not the same point, but at the output of that point in terms of g. All right, so this is maybe a little bit difficult to understand, so I think this is best understood through examples. The idea is, what if I want to determine the points at which a function is continuous for something like natural log of x squared plus y squared plus y plus 4? Right, so here this is a composition of functions. So we have natural log of u. This is like my outside function is natural log, and I know that's continuous, so long as u is strictly greater than 0, right? So that's when this function's continuous. What about u? What about the inside function? So u is equal to x squared plus y squared plus 4. And one thing to notice here, so this is continuous everywhere. And the other thing to note, so everywhere being all of R2, the plane. The other thing to note is that u, since x squared, y squared, those are non-negative, plus 4, so this will be positive. One thing to note here is that u, so I'll say notice, u is strictly greater than 0. So the output of u is strictly greater than 0 at all times. And so anything that I put into the natural log, any output here that's put into the natural log will be greater than, or the input will be greater than 0, and hence the function is continuous there. So this whole function is continuous for the entire plane. So this is continuous on all of the plane, all of R2. Because again, the inside function is continuous everywhere, and it's strictly greater than 0, which puts it into the domain of natural log, and natural log is continuous on that domain. So inside's continuous, outside's continuous at all the possible output values of the inside, hence the whole function is continuous on the plane. So h here is continuous on R2. All right, how about something like e to the x over y? So here again, I can specify my inside function. U will be x over y. Now that's continuous, except when y is equal to 0. So on that horizontal line, y equals 0. And then I have my outside function is e to the u, and that's continuous everywhere. Right, e to the xy is continuous everywhere. So what that means is that my entire function here, h, will be continuous everywhere except when the inside function is not continuous. So except on the horizontal line y equals 0. So this is continuous. H is continuous on R2 minus the line y equals 0. Or I could say, maybe I'll write that a little bit better. Continuous on the set xy in R2 such that y is not equal to 0. So we have to remove a horizontal line. We have to remove the x-axis, right? Y equals 0 is the x-axis. So we have to remove the x-axis from the plane, and our function is continuous everywhere there. All right, so not super complicated. The idea is to look at the inside, look at the outside, and figure out when those are continuous separately, and then use this theorem to tell us when the composition of the functions is continuous. All right, that's it for this video. In the next video, we're going to finally jump to functions of 3 or more variables, limits, continuity of those things. I'll see you there.